So today we'll be doing section 13.3 and 13.4. 13.3 is arc length, so that can allow us to find the length of a curve. And then 13.4 we do some cool stuff. We're going to check, just to explore motion in space, just a path of anything. It could be a golf ball. It could be any type of motion throughout space. We'll create the formula. We'll derive the formula together. Put the formula up here, and then we'll work some problems together from the practice set from the textbook. So hey, for length of curve, I thought the first curve we can get the length of. Let's get the length of a helix. The formula is we're going to take the integral from a to b, the magnitude of r prime of t. It's almost like you can think of it as the integral. This represents speed. Magnitude of r prime of t is speed. But we're going to take the integral of that. So they'll give you some vector curve. I thought we'd start with, let's start with one of those, a circular helix. I'm thinking, all right, how about cosine t, sine t, t. And let's just take this thing from 0 to 2 pi. I'm going to find the length of this curve, which is also the arc length with those limits of integration. Find the length of the curve. From t equal to 0 to t equal to 2 pi. So we'll definitely set up the two limits of 0 to 2 pi, right? But the first thing we need is r prime of t. So let's start with that. What's r prime of t? We call that the tangent vector, right? What would be the tangent vector for this? Hey, you don't have to draw a picture, but to get a sense of this picture, isn't that the circular helix, as I mentioned? Which axis does it spiral? X, Y, or Z? Can you tell? Yes, I heard it, the Z axis, everyone, right? So it's like I'll hide this. Ever see that circular relationship? It's like, oh, this curve travels on a circular cylinder. X squared plus Y squared equals 1, right? But then the Z component just has a variable t. Just as t increases, the Z component is going to increase. So it's just going to spiral up the Z axis. That's what that would look like, right? We just made a quick sketch. We're like, look at this thing just going like this. We're only going to go from spiraling from 0 all the way up to 2 pi, right? So it won't go too far. 2 pi is about 6.28 or so. What's r prime? What's the derivative of cosine of t?
Negative sine.
Negative sine of t. What's the derivative of sine of t?
Cosine.
Cosine of t. And what's the derivative of t?
1.
All right, so there's r prime of t. Now, we're going to write out the magnitude of r prime of t. Okay. So you're going to notice with this problem, everyone, we will be able to solve this. We will be able to solve this problem without the calculator. You can do it without the calculator. This length of curve of this helix here. I'm going to put the big square root, right? All right, what's that squared?
Sine squared.
So
Got t
the
plus.
negative squared becomes positive, right?
Mhm.
So I squared that component, this squared,
Plus cosine squared t.
and then 1 squared is
1.
boom. And we'll put this in the integral. We'll go from 0 to 2 pi, but look at that carefully. Before we put it in the integral, can you simplify it?
Yeah, square root of 2.
So let's see this. That's the trig out of any sine squared t plus cosine squared t is
1.
1. So you got square root of 1 plus square root of 1, or square root of 1 plus 1, which gives you a square root of 2. Does everyone see that? We're saying this was 1. Oh, so now this problem got really, really nice. I'm going to put this now in the integral. Go from 0 to 2 pi, square root of 2 dt. This will be the length of the curve. Easy integral for us to solve there. Not every problem so easy. There's going to be some. I'll reference them from the textbook. Even in directions, they'll say find the length of the curve, correct to 4 decimal places. They'll set you up to use your calculator and perform the definite integral because we wouldn't be able to manipulate that problem. like we did here. You know, when you deal with radicals, sometimes they can be neat. I got neat. Other times, you get an expression that we can't use just to use something to solve. What's the integral of square root of 2?
Square root of 2t.
Go from 0 to 2 pi. Okay, 2 pi times square root of 2. Minus, you plug in a 0 and you just get what? 0, so I wouldn't even write that. There's the length. So this is a cool section. Up until now, it's like you say, find the length of some curve. All we knew up till now was what, edge of a circle? Like circumference or an arc of a circle. Stuff we did in geometry class. But now we can find the length of any curve, which is kind of calculus. So just think of like a ball being thrown. You're like, holy cow, we can actually find the length of that. That ball got thrown from here to there. We can actually stretch that out and see what's that long length of that pass. If it was a football or baseball being hit, right? You're thinking of, who's that from the Orioles? Is it Davis? Who can smack the home runs? You're like, man, I can get the length of that ball. As long as we have a vector function that models that path. Now let's do another one, but this time I want to do a circular helix again. Okay, let's have it go down the y-axis. Okay, 3 cosine of 2t, 4t, 3 sine 2t. Get all this. This time, everyone, let's go from t equals 0 to t equal to pi. Let's find the length of this curve. Find the arc length from 0 to pi. That's also a circular helix. Even though this has 3's in front, and this has a 4t, you can still suck in this right here. Just check it out real quick. 3 cosine square root of 2t plus 3 sine square root of 2t. I just want you to explore this. Isn't this on a circular cylinder, the path of this curve? I'm just looking at the x and the z components and just looking at them. And if I factor out the 3, what do you now have?
Cosine square 2t.
Right? Oh, and I didn't square this, I apologize, so I'll square both of these. There's x squared plus the z squared, and let's just see what it turns into. I factor out the 9, and you got cosine square root of 2t plus sine squared 2t. And is that equal to 1?
Mm-hmm.
Great, so this is equal to 1. 1 times 9 is equals 9. So I just want to point out, this again, this circular helix travels on the surface of a circular cylinder. It's just going to have a radius of 3, right? X squared plus z squared equals 3 squared. I just wanted you to explore that. We'll do the math. But you can say, oh, this thing, but which axis does it spiral down? It goes down the y-axis, doesn't it? Is that 14? So we're just talking about some helix that goes from like 0 to pi, right? We have to start at just a rough sketch. It's like, okay, there goes this curve. We'll see how long it is. Okay. So start it out. First thing, get R prime. Be careful with chain rule. What's R prime of t?
So that should be 6.
6.
So negative 6 sine 2t.
Negative 6 sine of 2t. Very good. What's there, 14?
4.
Hear this? 6
Cosine.
cosine of 2t. So far so good? But again, watch. You'll be able to simplify this thing. You get the final solution even without it in the calculator. But after this problem, let's look at one where it's like, okay, we can't simplify it. Let's use a calculator. All right, what's the magnitude of our prime d? I get it. Whoops, let me get the square root ready. What is this squared? You gotta square that negative 6 too. 36 sine squared of 2t. What's that squared? 16. And what's this squared? 36 cosine squared. So before you go pulling out the calculator, setting up the integral from 0 to pi of this radical, see if you can break it down.
Square root of 52.
Okay, very good. You notice that 36, you can factor out of this sine squared of 2t plus the cosine squared of 2t. If you see that ahead of time, you don't have to show all this. I just wanted people to see why you're getting the square root of 52. Because this right there, once again, is just the value 1, right? You get the square root of 36 plus that 16 square root of 52. Or if you want to simplify it before you put in the integral, you can, but I'm going to leave it square root of 52. Maybe you just simplify that at the end. There it is. Ooh, again, it got really neat. I'm going to go from 0 to pi. What's the integral? Square root of 52t. Multiply by pi, you get square root of 52 pi, or what's that simplified?
2 root 13.
2 root 13 pi. Excellent. Any questions on it? Yes?
Why do we find the magnitude of the function?
In this case, we're finding the magnitude and then taking the integral because this is dealing with the speed. And so this came from just with the arc length. When you're talking about like the arc of a circle, I know it's going back to what? Radius s equals r theta from the circle. But in this case, the reason we're taking the speed, the integral of the speed, is because with the arc length of the like of a curve coming like this, we have to deal with what's the speed of this, whatever this particle is, and we'll find that integral. The derivation on this, it's a really good question, isn't a textbook. It's written in a textbook, but maybe at the end of this we could derive that after we do the 13.4. We'll definitely derive the formula for 13.4, but 13.3, I don't want to derive that one right now, but maybe if we have time at the end, we'll do that.
We did that in Calc 2, right? The arc length, like the derivation at the
Yeah.
end of Calc 2, yeah.
That's right. Anyone try this one? Find the length of this curve. You get, all right, t. Hey, I'm thinking from the textbook. It's got a t. E to the negative t, and t to the negative t. The limits, can you find the length of this curve from 1 to 3? Well, that's not a circular yoke. Find the length of that curve.
Just be careful with those derivatives, right?
What's our prime? What's that derivative?
1
1.
negative e to the power negative t.
Chain rule, right? What rule do you need?
Product.
We need product rule. See the t in front of that e to the negative t? So first, derivative second is a negative e to the negative t. Plus